Hey there, everybody. Welcome back to our unit for this week. We're going to be starting chapter 18 this week. We'll do part of it this week and part of it next week. So this week, we're just going to be kind of talking about the general processes of refraction, and how it applies, or some of the kind of optical phenomena that are associated with refraction. And then next week, we'll be doing more about the actual, like drawing the ray diagrams, having to do with lenses and all of that kind of good stuff, and some more stuff about the lenses as a particular application of what's happening with this. So we're kind of breaking this chapter down into two. I figured you could probably use a little bit of a break to split this into a little bit more time for you. So anyway, this particular one's all about refraction and some of the crazy stuff that happens. So now remember, refraction is the bending of light through different media, and it causes some pretty funky looking effects that I'm sure you have seen before. But we're going to go into a little bit more depth in this unit as to what causes those, or what some of the impacts of those particular things may be. So first things first is to kind of go back and make sure that we're defining kind of what refraction is. So refraction has to do with the bending of rays of light as they pass through different media. So up in the top right over here, this thing that's sort of in the middle here is a block of a particular type of really firm plastic called acrylic. And it's a clear plastic. It's used in bulletproof windows and some of those sorts of things. It's pretty optically clear, but yet you can tell that something's funky happens to that light as it passes through it. So we've got a laser beam coming down from the top, and then as it hits that border right there, you can see that it definitely takes a bit of a dog leg, and then it kind of straightens out again as it goes back out into the air. So this process, this bending, is called refraction. So there's some key terms that we need to have that kind of associate with this. And so I want to kind of point out sort of how we're going to use ray diagrams in this particular chapter. So what we've got, I'll explain what N here is in a second, but we've got boundaries between two different materials. They use the word interface in here, but we used to use boundaries. So like we'd have a boundary where there'd be air on one side and then this acrylic on the other side. Or we could talk about this side down here where there's acrylic on one side and air on the other side. That's fine. And then you've got your ray of light that's passing through this boundary. So again, just like what we did in the last unit, when we are drawing rays of light and drawing ray diagrams, we still always define our angles and things like that the same way. So what we've got is we've got an incident ray that's coming in here. And then we've got this dashed line is a normal line. It is perpendicular to the surface. And you can see that we've got our angle of incidence up here. So theta I is our incoming angle. Then as it bends outward, through that material, you can see that there's kind of a change in angle here. So now this is not the same like we did with mirrors. Remember in mirrors, we did the law of reflection where angle of incidence equals the angle of reflection. Here, we have an angle of incidence and an angle of refraction, and they're not equal to one another. You can see that theta I is greater than theta R. And again, we always measure our lines or our angles from the normal line. So again, similar to sort of how we're doing it, but again, now our rays are not bouncing off. They're passing through and bending as they pass through that different media. So why does this happen? Well, it turns out that different materials interact with light in different ways. And technically what it is called optical density, is kind of a nickname for it, although it's kind of a fake term. But really what's happening is that the light is changing speed. Light travels the fastest through a vacuum when there's no matter for it to interfere with. As it starts to pass through matter, there are different types of like I said, interference, some types of interactions that can slow the light down. Now, it's not a lot. You wouldn't necessarily see that difference, but we can see it when we're looking at what should be a straight line. Our eyes are really sensitive to this. A really great way to think about this is the lawnmower effect, and I'll put this up here in a second. But what you get is that as it's going from faster to slower, it tends to curve, or from slower to faster, it tends to curve. So again, I use the lawnmower idea is a really great way to kind of picture which way it curves. Imagine that you've got a lawnmower on concrete versus a lawnmower that's traveling through a really soft, plush, lawn. That as you've got that lawnmower is coming from the concrete, that concrete is a faster medium. And as soon as that lawnmower starts to drop off into that grass, that first wheel is going to kind of stick there a little bit. And the rest of the lawnmower is going to be able to kind of curve around it where it's hitting that. And it's going to cause that lawnmower to change its direction. And so what we would say, and the opposite happens when it's going from grass to concrete, but what we would say is that we talk about the light rays bending either towards the the normal or away from the normal. So if you think about this one up here, the sidewalk version of it, when it's on this faster medium, we've actually got a bigger angle between the light ray and the normal line. And then when it's in this slower medium here, we've got a smaller angle between the ray and the normal line that's on there. So we would say that in this case, that this is bending towards the medium. And then in this particular case, the opposite is happening, right? If we're talking about it's going, this direction now, starts in the grass and then ends on the concrete. Here's a narrower angle, and then as it goes into the concrete, it bends away from that particular normal line to it. So we would say in that case, it bends away from the medium, and this is a pretty consistent pattern. And then you can kind of see this down below here, pretty consistent pattern in terms of how this works. Get this out of the way. Get my pen back. That when it is in a faster medium, that it tends to bend away from the normal. It's curving away from it. And when it's in a slower medium, it's going to bend towards the normal. So you can always tell just kind of by looking at a diagram, which is the faster and which is the slower kind. So again, towards the normal in the slower medium and away from the normal in the faster medium. So when you take a look at this, you can actually, without knowing anything else about these materials, get some idea about the kind of optical density of these two particular materials. And yes, there are different types of rock, like calcite's one of them, or other types of minerals and things like that light can actually pass through. So you can kind of tell by looking at this which medium is which. So again, if you think about it, if it's more dense or slower, then you're going to have a smaller angle. It's going to be bent towards the normal. And as it goes into a faster medium, it's going to bend away from the normal. So that means between these two, between rock 1 and rock 2, this one down here is the faster one. And in this particular one, we say that this angle is bigger, and then this one is. I guess I should use 2 lines in there because they're not the same angle, right? Sorry, geometry people. But in this case, rock 1 has got the bigger angle, and rock 2, it's bending towards the normal. So that means this has to be the slower medium to it. So again, you can kind of figure out what's what by taking a look at that. And again, I go back to this concept of the lawnmower example to kind of figure out what it is. The slower medium, it's closer to the normal than it is in the faster medium. So slower medium, slower medium. However, how do we figure out what that difference is? Well, there's something that we can use to kind of characterize the difference. And this is something called the index of refraction. How big a difference is it between these two media? How much is it really slowing down that light? Because if you take a look at this one up here, that's a real narrow angle versus this is a pretty wide angle versus this is an even wider angle, right? It's going to depend on the relative kind of thickness, I guess, optical density of these two different materials. Well, that particular index, that measure, is called the index of refraction. So the index of refraction is relatively easy to calculate, and then I'll show you how we use this index of refraction on the next slide or two. So again, the name of this particular thing is called the index of refraction. Index of refraction in physics is abbreviated by a lowercase n, because lowercase n has already been used 8,000 times apparently, but anyway, it's called n. And what this is it's the relative ratio of the two speeds between them. So the top one is the speed of light unimpeded, or the speed of light in a vacuum, 3 times 10 to the 8th. The bottom one is the speed of light in that particular medium. So if it's slower, and it's always got to be slower than the speed of light, the optimal one, the lowest, I guess, index of refraction you can have is 1.00. That if you basically have velocity of light in a vacuum divided by velocity of light in a vacuum, you're going to have an index of refraction of 1. The speed of light in air is close enough that in 3 sig figs, it's still essentially an index of refraction of 1. It really doesn't slow down. Gases are so low density that light's basically unimpeded through gases. As the material gets thicker, so to speak, the material here, the velocity, slows down more and more. So if you have 3 times 10 to the 8th divided by a slower number, then you're going to get your indices of refraction are going to start to sort of bump up. Now, you don't really ever see huge numbers in here. I mean, they never go above 10. I don't think you ever really see it much above 2 to 3. I mean, diamond has a pretty heavy-duty index of refraction for typical transparent materials. There are some things that's higher, but not in a common circumstance. So your indices of refraction, oftentimes between 1 and like 2.5, really common range. So again, the bigger the number for the index of refraction, the slower the speed of the material. Common ones that we see a lot: air. I'm going to expect you to be able to remember that, but you've got a computer in front of you. You can look it up if you need to. Water, it's a little bit slower. And as you get into things like glass, and as you get into things like cubic zirconia and diamond, it gets even slower yet. So again, the index of refraction is simply defined as the ratio of unimpeded speed divided by the slower speed through the material that it's in. So when we're using this, this actually allows us, the phenomenon here, allows us to actually see transparent objects. I know it sounds really funny to say that, but if it weren't for the indices of refraction, the different indices of refraction between, say, air and glass or air and water, think about a clear glass of water, right? Those are both transparent materials. Why doesn't the water just disappear? Well, the reason is that we have all of these boundaries that we take for granted. Think about all the boundaries that are happening in this drawing right here. We've got air out here. We've got a glass boundary. We have a second glass boundary. It's probably made of a different kind of glass. And then down here, we have another material that's in here. This is something funky. And then notice this weird little thing that happened in here where that glass stirring rod actually disappeared. The reason why this happens, that we can see it up here but not down here, is that we've got light going through all different kinds of materials up in here. It's going through glass, and it's going through air, and it's going through other glass before it finally gets to our eyeballs. So it's bending a bunch of times, and we see those bends as edges. But down in here, where we actually have vegetable oil, and you can kind of see it in the middle here, and this particular type of glass, which is called Pyrex, it doesn't show up on my screen, they have essentially an identical index of refraction. So when you put this high temperature glass in here, this Pyrex, in this vegetable oil, because the light doesn't bend any differently around those edges, it appears to completely disappear. It's completely gone. And you can see that same effect in here. So here you've got a test tube made out of that same material. That test tube goes all the way down here. But what you've got is up in this part of the test tube is air. That test tube isn't all the way full. Down at the bottom here, this test tube has some of that oil that's in there, that vegetable oil. And then the whole container is full of vegetable oil. So you've got air out here. You've got a glass boundary and then vegetable oil, which you can kind of see that. And then you've got a second glass to air boundary here. But here, where you've got the glass to vegetable oil boundary, it looks like it completely disappears. So again, it's an interesting thing that these indices of refraction is what allows us to actually see different transparent materials because the light's actually bending between them. So in dealing with this, there's a fairly simple set of calculations that we can do called Snell's law that will help us kind of be able to either calculate the angles, like predict what angle something's going to bounce out as, or it can allow us to, a different way for us to calculate what an index of refraction is. So here's how this typically works. This is one of the ways that Snell's law gets presented. I think it's this way in the book. It's a set of ratios. Okay, fine. I tend to prefer it this way. It's a little bit easier to remember. N1 sine theta 1 equals N2 sine theta 2. So what this particular means is this is material number 1, say air over here, and this is material number 2, say acrylic over here. And what's nice about this is if I know some different information, like I know what N1 for air is. N1 for air, the index of refraction for air is 1.00. How can I figure out what sine theta 1 is? Well, all I'd have to do is get a ruler and a protractor, kind of set up my normal line right here, and I can measure this one right here, which is sine theta 1, or sine theta I in this particular case, and I can measure what that is and take the sine of it. Again, check to make sure your calculator is in degrees and not in radians. Then I can go over here and measure what is theta number 2. It's this one, the refracted one. I'll put a 2 here, and I can measure that from my diagram. And if I know what this one is, and let's say that one's like, I don't know, 50 degrees. It looks like it's a little bit more than 45. And let's say we know what this one is, and it's something like 35 degrees. And then I can just simply solve for whatever N2 is. So it's kind of a plug and chug sort of thing if you know what those pictures are. Again, you'll have to have a drawing. You'll be able to measure what your angles are. Or conversely, if I know what my two materials are, like I know what the index of refraction of air is, and I know what the index of refraction in the block is, I can predict what that new angle would be. Snell's law. Again, it's the rule, it's a mathematical equation that allows us to figure out changes in angle based on changes in indices of refraction. So with all of these, The math stuff that's in here, this being able to use Snell's law to predict it and being able to use the indices of refraction. We'll talk about that in our first Google Meet and do our practice some of the math that's on there and some of the drawing that's on there. So there you have it. Some of the introduction to refraction and some of the technical stuff behind it. Kind of what is refraction, that it's based on speed of light in different media, whether light bends towards or away from the normal. How do we calculate what an index of refraction is based on two different speeds? And then how can we use indices of refraction called Snell's law to be able to calculate or predict angles? There you go. Hope you liked it, and I will see you in part 2. Da, da, da.